All right, hello everyone. It's very late. It's February 17th. All right, let's just get this done and get one of the first. Usually it's gonna be an easy question. So yeah, I'll just get all these up. All right, minimum distance between BST nodes. Given the root of a binary search tree, return the minimum difference between the values of any two different nodes in the tree. Given the root, return the minimum difference between the values of any two nodes. Find the minimum difference between. This will be 1. Okay. So since we only have 100, let's just say 100. No, that's 2 to the 5, 2 to the 5th. Okay, so what does binary search tree help us to do this? Oh, we know the general distribution of things. So we want to find the minimum difference, right? What we can do is, like, these are larger, but the right subtree, the left tree of the right will be the biggest, because so what we can do is going from a root, right? For each node, we'll go to the left node and look for the rightmost node, right? And then we use that to compare with this, or we can go to its right and then go to the most left and use that to compare to this. So basically, what we can do is we start and then just, look for, the root is not likely, root is going to be the best option. I'm actually not sure. Or we can just traversal it. Yeah, I see what it's trying to do. It's a binary search tree, so you can just do left root right and then just compute. Yeah, okay. Yeah, I see what it's trying to do. Yeah, because the other way you can never be sure, right? You can never be sure. All right, let's see. Put this on out. Put this one in. All right, so what we're gonna do is if root, no. Right, if node, so we will go DFS node.left. Right, and then you're gonna say if node.left, right, self.res equals minimum self.res node.val minus node.left.val, and if node.right self.res equals minimum self.res node.right.val minus node.val, and then DFS node.right. So by doing this, for each one, I get the one right in front will get a one. This is actually not right, because this one right to the left to right. That's actually not right. That's actually not right. We can do this, but I need to return something. Because this is, I need to return. That's not right. That is not right. I need to return the biggest on the left and the smallest on the right. So L max, right? And then L max R min. I'm going to say if not node, we shall return. Oof. What do you return if not node? If not node, that's an interesting question. If not node, So I need to return two things, right? The max and, because I get the max, and then what should I return? I should return max and return the mean. Therefore, if not node, I shall return, let's say we'll return my the minimum and the maximum, right? The minimum and the maximum. So the minimum I can say, and the maximum I can say this, right? Otherwise, we can say left max, left min, right? And then you can say right max, right min. Right, with left max min, right max min, and then self.res equals minimum self.res. All right, so we want to use the left, so node.val minus left max, or right min minus node.val. That's, we update this, and then we return the minimum of I need to find the minimum of the whole thing, so it should be left min, right min, and node.val. Now node.val, I want to return the max, that actually is going to be right max, is going to be max, so I should just return right max. Right, I just return right max. Oh, I should not do this, right? Because I'm going to return right max, and that means the left min, right? That's what I return. The max on the right subtree is going to be the maximum of the whole thing, and the minimum on the left tree of the minimum of the whole thing. So on the left, we always try to find the maximum. So we want to find the maximum on the left. If on the right, we want to find the minimum on the right. And for this node, we want to find the maximum on the left. So yeah, so in this case, if it's a leaf node, right? If it's a leaf node, ooh, yeah, it's a little bit tricky, huh? What do? We say right max equals left min equals node.val, right? And then if node.left, update. If node.right, update. In fact, I think there should be left max equals right max equal left min equals right min. And if left, update. If right, update. And then we do this. Oh, then it will be the same. Nope. I think we should do it here. If I have left, I get the left max, right? If I have right, then I get right min. Once I'm done, I'll return this. Then I just need right max and the left min. Right? I think that should be enough. Let's try this. Oh, I have a none. What? Oh. How? I said if no dot left. That's interesting. Oh, my bad. I forgot to return. Forgot to return. Int inf is not. Oh, I forgot to run. Jesus, come on. It's like, what the hell? I forgot to run. DFS root. I don't even know what to say, man. Okay. Give it a shot. Yeah, I just like everyone return max. Every subtree returns the max and min value. And compare with the root value. With left max and right min. Okay, official solution equal to traversal without list. How did you traversal without a list? I was trying to do this, but I don't know how. Oh, assign it to pre-value. That's what That's what they do. They have something called pre-value. But you can just pass parent, right? Yeah, I think you can just pass parent. And this one don't have to return anything. If not node, I just return. if node, right, and self, and then dfs node.left node, and then self.rest shall equal to if parent, then self.rest equal to minimum self.rest. I mean from parent, so parent must be, hold on, this that's not parent. That shall be the previous node. So the previous node will always be bigger. Yeah, that shall be the pre. So it's always gonna be pre.value minus node.val, and dfs pre-node is going to be, so when I say pre-node is bigger, right? Because we go left, we're on the left, that's current node, so it's bigger. Now if we go right, isn't the pre-node is going to be the current node? Oh, the pre-node is going to be, no. We go this, right? We go left to left to left to left. Right, once we're done, we will return. Yeah. Oh, it's node.val. Yeah, we put node into it, so node.left, and node.left is smaller. Right? So I had a previous bigger, so pre minus this. But once we hit, now we go to the right subtree. We go right. But we also go this. Yeah, this is right, because the pre is always going to be bigger. And now we just do node dot right in node. Right? We go node dot right, and now we go node dot right. We just keep go left. And once we finish, the node dot right, the pre is actually smaller than me. Right? So what if I don't have any on the left? Then the parent is actually smaller than me. I got stuck here. Yeah, we go left, left. Now we're with the right node, right? Okay, now we are the right. Who's the next node on the right? We don't know, we just go all the way down. No, I don't think that's the way to go. I think I'm gonna use a global. Okay. And then here's what we're going to do. So the pre is actually smaller, right? When the size is going to be smaller. So if visit to the node, this node is going to be the pre. So it's going to be node.val minus pre.val. And after that, I can say self.pre is going to be node. This is the previous node. Then we don't need any of this. That shall be right. Yeah, I'll get a global going. And parent is not, there's no parent. It's like really late, and then the ability to think just tanks. Like literally tanks. Alright, so yeah, I'll do another one. Minimum common value. 2 integer arrays. Non-decreasing order to the minimum integer common to both arrays. Note that an integer set is common to both if both arrays have at least one. So we put pointer, right? If one's bigger, we move the other one. If that one bigger, move this one until the 2 points are the same. And if one is out, that means there's no common. Okay, ij equals 0. Okay. While I smaller than line num1 and j smaller than line num2. If num1i is equal to num2j, return num1i. Otherwise, if num1i is larger, well, smaller is fine. Num2j I plus equal 1, else plus equal 1. And then if 1 gets out, and now we just return minus 1. Oh. Okay. What is it called? Merge sort. Minimum operation to make array equal. You're given two integer array, num1, num2. If equal length and integer k, you can perform the following operations on num1. Choose two indices and increment nums I by k and decrement nums j by k. Okay, nums1 is set to be equal to num2 if all indices I, such that this and these two are same. Return the minimum number of operations required to make these two equal. If it's not possible, return -1. So we can minus this one. Oh, no, num1 need to be plus. Num2. Wait, hold on. What? Two indices and increase this. Oh, all num1. All num1. And one is increase, the other is decrease. So this one decreased by 3. This one increased by 3. This one decreased by 3. I 2. This one increased by 3. 0 decreased by 3. And then 0 and 2 and 3. Yeah. This is not possible. No idea, but give it a shot. So basically what we're saying is we want a pair in num1, right? We want a pair in num1. So num1, what we have in num1 is 4, 3, 1, 4. And num2 is 1, 3, 7, 1. So what we do is to do a bunch of operations. So this one, we minus, and it's if we minus and plus, that's kind of wasteful, right? I don't think that's, I don't know, because you might want to do, because you plus. So each operation, so you can always plus, and always you can plus minus, right? So you find one to plus and find one to minus. And if you want to find another one to minus, you can put this plus. Then why don't you just pair them up? Right? You can pair them up. If you pair them up, you don't have to do on the same thing. So if we can do, we don't have to do on the same thing, which means all the numbers that need to be changed shall be changed. The numbers that do not need to be changed should not be changed. Yeah, because if you have odd number to change, if you have 1 that needs to be changed, then it's not possible. No matter what, it's not possible, right? If the difference is on one position, then if you want to change that position, and no matter how you change, because you add this, someone has to decrease, right? And you have to change that, and someone, so that's not possible. So it will only be possible if the difference is even. That's actually not true, because you can add twice on something. See what I'm saying? Is that if it's one difference, that's not possible. If it's 2, if it's 3, you got more that to share around, and that's possible. Okay, so then you have something need to add and something need to minus, right? So you need to add and something need to minus. Basically, you're moving something from one to the other. Yeah, you're moving something from one to the other. You're moving 3 to here, 3 to here. So we can do a sum, right? If we do a sum, and the sum is not different, this is 15. No, this is 18. This is 13, so it's not possible, right? No matter how you move, it's not possible. These two are the same because this is 12 and this is 12. So we can sum them to get a basic idea, right? So now sum them if they're the same. Then you can consider, okay, how can we make them move? Well, like I said, you're moving something to the other and you don't want to move it back, right? So you always want to move something to some place that's needed. Yeah, that's why only one difference is not going to work. That's perfectly fine. So now you need to find which position needs to move. The one that do not need to be changed, you don't need to change. So in the first case, we have the first position 0, position 2, and position 3. And these need to be moved, right? So now you look at the first one. If it needs to be decreased, then it has to be decreased. And you can actually say, because it has to be k, every time it has to be k. So if the difference is not a multiple of k, then it's not possible. right? The difference has to be a multiple of k. And if like I say, man, it's just not possible because every time you have to add k, right? You have to add k or remove k to reach that value. There's no other way. So, okay, so you can also find the difference between them and then just see if each difference is divisible by k. So I can find, so we have plus and minuses, right? So I can say the first one minus the second one. Okay, so I have a plus 3, which means you need to remove 3. Actually, it'll be the second minus first will be easier to do. So we have to remove 3, we have the plus 6, and I have to remove 3. Right, so I have this plus minus. And everything has to be divisible by k. If anything is not divisible by k, that's not possible. Okay, now everything is divisible by k. Okay, it is divisible by k. And then we need to know, how do we organize this? So we have some minuses, some pluses, right? So basically all the pluses will go to, all the minuses will go to the plus, right? All the minuses will go to the plus, right? Because they have to move, and then we know they're equal, right? They're equal. So what we can do is, yeah, it's deterministic. Like if you need to plus 6, you have to move 2 times. All right, it's just you have to move 2 times. So you find all the pluses, right? Because yeah, you find all the pluses, or you find all the minuses. It doesn't really matter. You find all the pluses and then just see how many pluses you need. Yeah, you just go to the plus or go to the minus, because each minus you have to do it that many times, right? And then you just find out. If I have 2 minuses, you have to go to 2 times. You have to have a minus 6, a minus 3, right? You know the minus 6 I need to take 2 times, and each of this minus, it does not affect the other minus. It'll minus go to plus, right? So basically, I think the answer shall just be, if I'm not mistaken, the answer shall just, first of all, if sum nums1 is not equal to sum nums2, that is going to return a -1. That's not possible. Okay, and then you're gonna do diff equals for n1 and 2 in zip num1 num2. It doesn't really matter. I can do n1 minus n2 minus n2, right? That's the difference. And say any for d in diff d k. Actually, I don't know. Yeah, it is upon -6. Yeah. So this is equal to, is not equal to 0. If any of them is not equal to 0, then I'll return -1. Okay, now they are all equal to 0. Then we just need to find, all the positives or all the negatives. All the positives. So we shall return, say, sum for d in diff if d is larger than 0. Ooh, and then if n1 is not equal to n2, right? And then if it's larger than 0, and then we just do d divided by k, something like that. Okay, let's give this a shot. right there. Yeah, I think we're there. Let's try this. Integer division by 0. Oh, shoot. Jesus. Oh, Lord. If k is 0 and diff, return -1. That is an edge case. Didn't even pay attention to. Oh yeah, k can be 0. Dude, this is... Oops. Press the wrong button. I think it's a 0. It was -1. And we can actually try another one, right, to make sure. Actually, if why did I do this? If not diff, right, which means everybody is the same, then it's always going to be 0. And then if this, which we have, then it's going to be this. All right, try this one. Okay, not bad, not bad. It's deterministic. This is determined. Just analyze it step by step. All right, I think that'll be it.